After studying this module, you shall be able to understand the biological growth function of renewable resources and the concept of steady state harvests, learn the process of arriving at bioeconomic equilibrium, outcome in an open access fishery and static private property fishery, undertake comparative static analysis for open access and private property models, analyze the role of property rights in optimal use of renewable resources. Environmental resources are generally divided into two broad categories: renewable resources and exhaustible resources. The resources that have the capacity for reproduction and growth are generally known as renewable resources. It is important to distinguish between stocks and flows of the renewable resources. The stock is a measure of the quantity of the resource existing at a point in time, measured either as the aggregate mass of the biological material, the biomass in question, such as the total weight of fish of particular age, classes, or the cubic meters of standing timber, or in terms of population numbers. The flow is the change in the stock over an interval of time where the change results either from biological factors or from harvesting activity. Renewable resources includes biological organisms such as fisheries and forests which have a natural capacity for growth, and water and atmospheric systems which are reproduced by physical or chemical processes. Solar, wind, wave, and geothermal energy are also considered as renewable. Arable and grazing lands are also classified as renewable resources as their fertility levels can naturally regenerate so long as the demands made on the soil are not excessive.
The management of natural resources is an extensively researched topic in environmental economics. The principal economic question in the optimal use of renewable natural resources has been regarded the harvesting of renewable resource in the present and future time periods. In this context, it is also important to draw one basic similarity between renewable and non-renewable resources. Prolonged harvesting and extraction activity can bring down the stock levels of both types of resources to zero.
Open access resources tend to be overexploited in both biological and economic sense. If the access can be restricted through appropriate property rights, the resources might not get overexploited to the extent of near exhaustion. Non-renewable resources may exhaust due to their finite stocks, whereas a few renewable resources may exhaust if the rate at which they are harvested exceeds the rate at which they replenish themselves. The exhaustion of renewable resources can be linked to the absence of enforceable property rights, regulation, or collective control over harvesting behavior.
Literature on the economics of renewable resources largely revolves around fisheries and the economics of forestry. Most forms of renewable resource exploitation can be analyzed using certain modifications in fishery economics. Fishery economics can be studied under two sets of institutional arrangements. First, an open access fishery and a profit maximizing fishery, in which enforceable private property rights exist. This module shall principally deal with both the institutional arrangements of fishery.
Investigating the pattern of biological growth of the renewable resource is the first step taken in order to study the economics of any renewable resource. It is first necessary to describe the pattern of biological or other growth of the resource. Suppose that the population stock is S and it grows at a fixed rate. G denotes the intrinsic or potential growth rate of population or fishery, which can essentially be seen as the difference between the population's birth and natural mortality rate. This is the proportional rate at which the fish stock would grow when its size is small relative to the carrying capacity of the fishery. Then, in the absence of human predation, the rate of change of the population over time is given by ds by dt, which is identical to s dot, which is further equal to gs. Now let's suppose that under a given set of environmental conditions, there is a finite upper bound on the size to which the population can grow. We will denote this as S max. We may therefore write the biological growth function as S dot identical to ds by dt, which is equal to g multiplied by 1 minus s divided by S max into S where g is greater than 0. Now, to refer to the net effect of natural changes and human predation, the module shall use the alternative symbol Gs, as G depends upon S, to refer to stock changes due only to natural causes. With this change, the logistic biological growth function becomes G into S equal to G multiplied by 1 minus S divided by S max into S. This notation defines a logistic growth function for the case where the species does not possess any non-zero lower threshold population level. Biological growth function that can capture the natural growth process of many fish, bird, and animal populations is the logistic growth function, and hence it has been extensively used in literature. Let's now study about the concept of steady harvest. For a period of time, the stock being harvested, H, remains equal to the amount of net natural growth of the resource, G, and these magnitudes remain constant over a sequence of consecutive periods. It is called the steady state harvesting. The constant magnitude being harvested is called the sustainable yield. Using the notations described earlier, S dot being the actual rate of change of the renewable resource stock, and hence S dot equals net natural growth of resource minus stock being harvested. A steady state harvesting is denoted S dot is equal to 0, and so the resource stock remains constant over time. Let's now look at two different steady state harvests. Let x-axis denote the stock of resources, y-axis denotes net natural growth of resource. The inverted U-shaped curve is the logistic growth function for the resource, fish in our example. The logistic growth model implies that an environmental system will have maximum carrying capacity S max. There is one particular stock size S MSY at which the quantity of net natural growth is at its maximum G MSY. If at a stock of S MSY harvest is set at the constant rate H MSY, then the steady state maximum sustainable yield MSY can be obtained. However, HMSY is not the only possible steady state harvest. There may exist other feasible steady state harvest between 0 and HMSY that can be supported by any stock between 0 and Smax. For example, H1 is a feasible steady state harvest if the stock size is maintained at either S1L or S1U. Optimal management of renewable resources like fishery, forest must involve strategies to ensure maximum sustainable yield. In the literature of environmental economics, open access fisheries share a few features of standard perfect competition model. First, large number of independent fishing firms is involved in exploiting fishery for commercial purposes, and hence each fishing firm takes the price of fishery as given. Second, there are no impediments to entry into and exit from the fishery. However, the free entry assumption in open access fishery comes with an additional rider of no enforceable property rights to the in situ fishery resources, including the fish in the water. But firms do have individual property rights to their fishing capital and to any fish that they have actually caught. Moreover, if any firm chooses to leave some fish in the pond, contemplating investment to enhance growth of fishes, that firm has no enforceable rights to the fruits of that investment. Any firm that catch the fishes at any future date owns the fish and keeps its catch. Algebraically, the open access model has two components: a biological submodel describing the natural growth process of the fishery, an economic submodel describing the economic behavior of the fishing boat owners.
The analysis involves arriving at steady state equilibrium, which consists of a set of circumstances in which resource stock size is unchanging over time, that is, a biological equilibrium, and the fishing fleet is constant with no net inflow or outflow of vessels, an economic equilibrium. Because the steady state equilibrium is a joint biological economical equilibrium, it is often referred to as bioeconomic equilibrium.
Logical submodel. In the absence of harvesting and other human interference, the rate of change of the stock depends on the prevailing stock size. ds by dt is equal to g into s. Let's now focus on the harvest function or fishery production function. Harvest function may depend on the amount of resources devoted to fishing. The size of the harvest is assumed to depend upon one magnitude called effort, E. Harvest may also depend on the size of resource stock referred to as S. Other things being equal, the larger the stock, the greater the harvest for any given level of effort. Hence we obtain H is equal to H into E and S. The relationship between harvest, effort, and stock can take a variety of particular forms. One very simple form appears to be a good approximation to actual relationships and is given by H is equal to E into effort into stock, where E is a constant number, often called the catch coefficient. Divided each side by E, we have H by effort equals E into stock, which says that the quantity harvested per unit effort is equal to some multiple E of the stock size. The growth function of fish stock with human predation can take the form of the biological growth function less the quantity harvested, that is S dot equals G into S minus H. Harvesting effort supplied in open access fishery depends upon the level of economic profit prevailing in fishery. Economic profit is the difference between the total revenue from the sale of harvested resources and the total cost incurred in resource harvesting. Free entry of firms into open access fishery continues, thereby increasing the harvesting effort as long as it is possible to earn positive economic profit. The change in harvesting effort as a dependent on level of economic profit can be algebraically shown as dE by dt is equal to delta NB, where delta is a positive parameter indicating the responsiveness of industry size to industry profitability. When economic profit NB is positive, firms will enter the industry, and when it is negative, they will leave. The magnitude of that response for any given level of profit or loss will be determined by delta. Biological equilibrium occurs where the resource stock is constant through time, that is, it is in a steady state. This requires that the amount being harvested equals the amount of net natural growth, G is equal to H. Economic equilibrium requires that the amount of fishing effort be constant through time. Such an equilibrium is only possible in open access fisheries when rents have been driven to zero, so that there is no longer an incentive for entry into or exit from the industry, nor for the fishing effort on the part of existing fishermen to change. We express this by the equation NB is equal to B minus C is equal to 0, which implies, under our assumptions, that pH is equal to WE. Notice that when the condition pH is equal to WE is satisfied, dE upon dt is equal to 0, and so effort is constant at its equilibrium or steady state level E is equal to E star. Let's now graphically explain the steady state equilibrium yield effort relationship. The x axis measures effort and y measures harvest of resource level. The inverted U-shaped curve here portrays the steady state harvests that correspond to each possible effort level. It describes what is often called the fisheries yield effort relationship. Mathematically, it is a plot of equation H equal to constant E into effort E into S max into 1 minus E by G into effort E. For example, at an effort level of EPP, there is a steady state harvest level of HPP meet at point 1 tangent to the curve. The particular point on this yield effort curve that corresponds to open axis equilibrium will be the one that generates zero economic profit. And to find the zero economic profit, we shall consider the zero economic profit equilibrium condition PH is equal to WE, which can be written as H is equal to W upon P into E. For given values of P and W, this plots as a ray from the origin with slope W upon P. The intersection of this ray with the yield effort curve locates the unique open axis equilibrium outcome given by HOA and EOA. Let's now graphically explain the steady state equilibrium yield effort relationship. The x axis measures effort and y measures harvest of resource level. The inverted U-shaped curve here portrays the steady state harvests that correspond to each possible effort level. It describes what is often called the fisheries yield effort relationship. Mathematically, it is a plot of equation H equal to constant E into effort E into S max into 1 minus E by G into effort E. For example, at an effort level of EPP, there is a steady state harvest level of HPP meet at point 1 tangent to the curve. The particular point on this yield effort curve that corresponds to open axis equilibrium will be the one that generates zero economic profit. And to find the zero economic profit, we shall consider the zero economic profit equilibrium condition PH is equal to WE, which can be written as H is equal to W upon P into E. For given values of P and W, this plots as a ray from the origin with slope W upon P. The intersection of this ray with the yield effort curve locates the unique open axis equilibrium outcome given by HOA and EOA.
In an open access fishery, the firms tend to exploit available stocks as long as positive profit is available. From the perspective of the fishermen, allowing fish stocks to recover and grow by reducing the catch today is in the collective interest of all. However, no guaranteed reward for the restrainer fishermen in terms of higher catches later prevents him from individually restricting the fishing effort. From a social perspective, open access fishery tends to overexploit the resources, posing danger for the stock of fishery to reach biological dangerous levels.
Private property rights can provide an institutional framework to tackle the problems like overexploitation of the resource or posing danger for the stock of fishery to reach biologically dangerous levels. The private property fishery has the following three characteristics. There is a large number of fishing firms, each behaving as a price taker and so regarding price as being equal to marginal revenue. It is for this reason that the industry is often described as being competitive. Each firm is profit or wealth maximizing. There is a particular structure of well defined and enforceable property rights to the fishery such that owners can control access to the fishery and appropriate any rents that it is capable of delivering. Economic literature offers many variants of private property fishery. This module shall cover only the static profit maximizing private property fishery model. The static fishery model estimates the aggregate level of effort, stock, and harvest that can be achieved at an arbitrarily chosen period of time in a setup where the individual profit maximizing firm operates with enforceable private property rights. The analysis supposes that biological and economic conditions remain constant over some span of time. This way of dealing with time in effect abstracting from it and looking at decisions in only one time period, but which are replicated over successive periods, leads to its description as a static fishery model. More specifically, the static private property fishery turns out to be a special case of a multi period fishery model, the special case in which owners use a zero discount rate. The biological and economic equations of the static private property fishery model are identical to those of the open access fishery in all respects but one. The open access entry rule dE upon dt is equal to delta into NB, which in turn implies a zero profit economic equilibrium no longer applies. Instead, owners choose effort to maximize economic profit from the fishery. Let us now graphically show the effort level at which owner will try to maximize his profit. The x-axis measures effort and y measures revenue. We multiply both functions by the market price of fish. So the inverted U-shape yield effort equation then becomes a revenue effort equation, and the ray emerging from the origin becomes pH is equal to WE, with the right hand side thereby denoting fishing costs. Profit is maximized at the effort level, which maximizes the surplus of revenue over costs. Diagrammatically, this occurs where the slopes of the total cost and total revenue curves are equal. This is indicated by the tangent to the yield effort function at EPP being parallel to the slope of the H is equal to W upon P into E line. Thus, the static private property equilibrium leads to a higher resource stock than that prevails under open access. The level of effort is also lower in comparison to open access model, thereby suggesting less exploitation of fishery in private property model under the assumptions made about functional forms. Open access regimes usually give inefficient outcomes.
In this module, you have learnt about first, the logistic growth equation that can be used to trace the biological growth process of renewable resources. Second, the module captures the example of fishery under two institutional arrangements, open access and private property regimes. Harvesting of renewable resources can be analyzed using the concept of sustainable yield. Open access fisheries share some of its features with perfect competition, and open access fishery is likely to be characterized by an economically excessive amount of fishing effort. Economic and biological overharvesting are more likely to occur where the stock is exploited under conditions of open access than where access can be regulated and enforceable property rights